So next we have a flow chart on how to design a shaft, okay? So, and you see here that I made 3 boxes. So you might need to go through this flow chart in your own time, step by step, and see what is in there. But today we are going to focus on section number 1, section number 2, and section number 3. And next time we're going to focus more on fluctuating loads. So the idea is that as if we are broken down the design of a shaft into stages or sections or parts, okay? So in section number 1, we are going to talk about how to determine the external loads. For example, if you have a set of gears, so how you can determine the loads between the gears and how those loads are going to transmit to the shaft and consequently to the bearings. Choose preliminary dimensions of the gear based on the geometrical constraints. You need to identify the critical sections where the stresses are quite high. And then we start by studying the steady state loading. So the idea here is that first we are going to assume that we have steady state loads, and then we are going to define an initial diameter for the shaft. Then later you will get to understand that loads are of fluctuating nature on the system, and then we have to design against fatigue. But we can use this diameter that we have found based on steady state or static loading in the fatigue as well. We'll just see how we can link these two together. So we find an initial diameter from here, and then we verify the diameter using fluctuating loads and make sure that it does not fail due to fatigue. But this is our first point, and this is the second. So we start from here, and then we go to here. So first, we are going to go through the steady state loading. In the second section, we are going to talk about the internal moments and forces, like if we have torsion, if we have bending, and how we can combine these two stress types together. We're going to talk about the factor of safety, and then compare the factored stress, which is the stresses that are developed through or due to the loadings on the gears and shaft, and then compare it to the strength of the material. So these are the 3 main sections that we're going to talk about today. And then later, next time, we're going to talk about fatigue. So you see here, I put section 1. So I'll go section 1, 2, 3. So in section 1, the first part is to determine the external loads exerted on the shaft. And the graph here, or this figure here, shows you typical applied loads on a shaft. So for example, we have transverse loads. Okay, these are something similar to the radial load that is coming from the spare gear. Then this makes the shaft or just deflect the shaft. So, and then because of the bending. So transverse loads cause bending, and bending cause lateral deflection. Also, when you transmit power from, for example, motor to a driven machine, so you transmit this power through a torque. So you apply a torque. You apply a torque to the shaft. So you have torsional load here, and then due to this torsional load, we have twist. So because the shaft has elastic nature, so it twists. Also, you can have axial loads. These axial loads can be coming from, for example, if you have helical gear, if you have a worm and worm wheel, or if you have a bevel gear, so it develops some axial loads. So these axial loads can be developed as well. So here, more explanation about torsional load, transverse loads, axial load, where they are coming from. But this is what I have explained on the previous slide. We are still in section 1. So the second part is to choose what's called the preliminary dimensions of the shaft. Actually, this depends on the geometrical and functional requirements of the system and on the bearings as arrangements. You have seen, based on what I have shown you so far, that bearings take some space as well. So you need to allow for some space for bearings, okay? you need to consider the existing designs. Then the second part in section number 1 is to identify critical shaft sections. I'm sure that you've studied so far what's called the bending moment diagram, the shear force diagram. So what we do here, we just start calculating stresses based on the loads that are applied on the gear shaft. And then we define those critical locations. So those critical locations where the stresses, where we have stress concentration, for example, where we have maximum stresses, where torque is present, where there is a shoulder in the shaft, so that generates some sort of stress concentration. Okay, so this is what we are going to try to do. We just draw the shaft, and then apply the forces that is coming from the gears, for example, and then try to draw the bending moment diagram, the shear force diagram, and based on that, we identify the locations where the bending moments are quite high, the shear due to torsion is quite high, and then we identify those places as the critical locations on the shaft. Okay, so they are also associated with points of load application. So when the load is applied, at some point, this is considered as a critical location. So critical locations where stresses are maximum, loads are applied, stress concentration due to sharp edges. These are kind of the critical sections on the shaft we need to consider for design. So the arrangements of bearings can have an effect on the how the shaft is going to deflect as well. And you have to just examples here. Let's say this is A and this is B. Okay, so this in the first one at the top, A. So you have a shaft. So this is a shaft. So it's just it shows you that it is continuous here, but because it's quite long, so we are just considering only the right and the left-hand sides. But this denotes that the shaft is continuous here between these 2 points, okay? On the left-hand side, you see some arrows. So it means that in this direction, the shaft and the bearings can take the axial direction, can take the axial reaction. So if the forces is pushing this to the right-hand side, it does not move, right? But you see here, you have flat surfaces here. So it just means that in here, it is free to move to the left and to the right, okay? And again, please remember the step that just here in the shaft, so that this bearing or deep groove ball bearing does not move in this direction. So it is supported by this shoulder here. It is supported by this shoulder and this shoulder. And on the right-hand side as well, you have a nut here and some sort of, so it does not move to the right as well. So you have a screwed here, screwed portion, so that you have a nut and screw, and this part does not move in this direction. If you look at B, you will find that if there is a force pushing this arrangement to the right, so there is a reaction between because of these like shoulders. So the bearing does not move to the right. And if you have force coming from the right, so due to the arrangement here, so the shaft and the bearing does not move. So there is a reaction force in this direction, and then there is a reaction force on the other direction as well. So in this case, this is kind of similar to the one with roller. If you remember, we keep like drawing something similar to this to you. So it is something similar to that. And here it is something similar to that. It is constrained in X and Y direction here for both ends, but here it is constrained in Y direction, but it can move in the X direction. So this is the starting point of section number 2. Okay, so in section number 1, we spoke about these different things. But in section number 2, the first part is to try to find the internal moments and forces. Okay. Then I'm going to consider here 2 cases because they are quite relevant. The first one is spur gear, and the second one is the helical gear. If you have a driving pinion and then you have a driven gear here, then the driving pinion rotates in the clockwise direction and the driving gear rotates in the counterclockwise direction. There is a force between them that tries to push them apart. It's called the radial force or the separating force. And then there is another force that is the tangential force. You have a tangential force here. And the direction of the tangential force is quite important because if you go to the pinion, for example, the direction of WT is opposite to the direction of rotation. And if you go to the pinion, to the gear, if you go to the gear, you'll find that the direction of WT is goes with the direction of rotation, right? And then these 2 forces, WT and WR, they are perpendicular. So WN here is your resultant force, and the angle between the resultant force and the tangential force is phi, which is the pressure angle. So first, you find the tangential force based on either the power or the torque, and the tangential force is the same on the pinion and on the gear. They are opposite in direction, and they are the same in magnitude based on Newton's third law. So the tangential force here is equal to the torque divided by the radius of the pinion, for example, where the radius of the pinion here, so it is the torque divided by the diameter of the pinion divided by 2. That's why here you see it's 2t divided by d. So this 2 goes up, so it's 2t divided by d. Either you are calculating this based on the diameter of the pinion or the diameter of the gear, so you can use d here. There is, based on this triangle here, there is a relation between the radial force W sub r and the tangential force W sub t. So WR is equal to WT multiplied by tan the pressure angle. So this is quite simple now because I assume that you have seen the previous video that I've explained this in detail. So I'm going to go now and talk about the helical gears. So what if you have a pair of helical gears? So on top of the radial force and the tangential force, we have also axial force. So this axial force is developed due to the nature of the tooth. So I'm going to start by the left-hand side graph here. And then the first point is that we assume that we have a tooth. And then this tooth goes with a specific angle with the center line of the gear. So if I just draw here, for example, a side view of the gear, let's say this is the side view of the gear, and you have a center line here, okay? And then you have the teeth are going in a specific direction with the center line. So the angle here between the tooth and the center line here is alpha. In this case, sometimes they call it beta. Okay, so this is defined as the helix angle. So it is the angle between the tooth and the center line. Okay, then due to this nature, the contact force, the total or the resultant force is going to be perpendicular to this tooth. So this force here is what we defined as Fn. So Fn here is perpendicular to the tooth, okay? But this Fn is a three-dimensional force. It is coming in the space. So as you see here, so you see here Fn, then this Fn can be resolved into three different components. One component is Fr, another component is Ft, and the third component is Fa. Fa is very simple. It goes along the center line. So Fa here, the force Fa is parallel to the center line of the gear, right? And then the Fr is the radial force, again, it is kind of trying to separate the two gears from one another. And the FT here, so again, if I draw the pinion and the gear, so I would have here FR in this direction, and then again FT tangent. So we have already got these, but on top of these, we have here, we have a radial force. And the radial force here, either it is going out of the page or going inside the page based on this graph, okay? So here we have three forces. We have FT, we have FR, and then we have FA that is parallel to the center line, if this is the center line of the gear. So this Fn, if we focus on this triangle here, okay, so which is this triangle here, so it's ABC, you will find that the angle between the total normal force Fn and the BC, the segment BC, the angle here is phi n, where phi n here is simply the normal, it is the normal pressure angle. It is the normal pressure angle because this ABC D plane is called the normal plane. ABCD plane is the normal plane. You see here, you can find the relation between FR and Fn. So based on this Pythagoras theorem, so FR is equal to Fn multiplied by sine phi n. Phi n here is again is a normal pressure angle because it is in the normal plane, where the normal plane is perpendicular to the teeth. Okay. Then BC here based on the triangle is Fn cosine phi n. So I have two equations based on this plane, the normal plane that is perpendicular to the tooth. If you look from the side view, okay, so you will see two circles, right? Similar to the spur gear. So you have one circle here, you have another circle here, okay? So you are looking from the side view, and now what you have the pitch circle for the pinion, which is this one, and the pitch circle for the gear, which is this one. And then when the power is transmitted, so there is kind of a torque here that is transmitted from the pinion to the gear. So this pinion rotates in the clockwise direction, and then the gear rotates in the counterclockwise direction. So in general here, we have two forces, two main forces. The two main forces is the force that tries to separate these two gears from one another, regardless of either we have spur gear or helical gear. So there is a radial force, which is the FR here, that tries to separate these two gears. This FR, there is one more FR in here that goes to the second gear that is above this. So if you consider that this is only the driven now, okay, or the gear. There is on top here we have the pinion as well. It's not shown for simplicity, okay? So this FR here, there is another FR that is going opposite to that, right? So these two FRs are here, okay? Then we have another force that is tangent. So this the force that makes the gear rotates. This is the force. This component FT is tangent to the circle, is tangent to the pitch circle, and makes this gear rotates. Okay, so this is FT. So this is this component here. Okay. On top of that, because of the nature of the teeth here, it has specific angle with the center line, as I've shown here on the right-hand side. There is another force that is generated as FA. This is the axial force. So eventually, what you have Fn. This Fn is like a three-dimensional force. It is coming in the space between the two teeth. And then if you were to resolve this Fn into X, Y, Z, so you will have Fa goes along the center line of the gear, and then you have Fr that is coming and separating the two gears, and you have Ft that makes the gear rotate. So these are the three forces that generate or that are generated due to the meshing between these two teeth. I think you need to, maybe you just need to try to visualize this a little bit. I know it's quite challenging, but eventually I'm sure that you will be able to get. So if I go back here, so if we focus on this plane here, okay, so in this plane or this triangle here, so we have the triangle FCB, where this side here is parallel to FA, so I'm going to call this FA, and then this side BC is based on the previous slide. If I go to the previous slide, you see here we have this side BC, and then we have an equation for BC. So BC for us is known. So we know BC, and then we can, based on that and based on this triangle, we can try to find a relation for FT and FA. This angle alpha is this angle here, is the angle between the teeth and the center line. It is the helix angle. So based on this triangle, the Pythagoras theorem again is FT is equal to BC cosine alpha. And then based on that, we can go back, substitute this equation number 2 into equation number 3, into this equation. And then so we just replace BC by Fn cosine phi n. And then based on here on this triangle as well, you find that FA, so BC sine alpha based on, and here as well, this is BC. So this is BC cosine alpha and BC sine alpha based on this triangle here. And then the BC can be, the BC is Fn cosine alpha n, BC and cosine alpha. We just substitute this BC value into these two equations. And then eventually you will find that you need to make some math here to just relate these three forces together. So FR as a function of FT, FA as a function of FT, and Fn as a function of FT. So the idea is that FT can be found using the 2T over D, because normally the torque is given and the diameter of the gear can be found. Then FT is known. So and also these values, the helix angle alpha, the normal pressure angle phi n are known. So we can simply find FR, or the radial force. Once we find the FR, we can also, based on the value of FT and the helix angle, we can find the axial force. And based on the value of FT and these two values, we can find Fn. Okay. So the last thing here, if we consider this section here, if we consider here this triangle, this is the EFC. This is in the normal plane, sorry, transverse plane. Okay, so in this case, we have this side as FT, and then the vertical here side is, because we have cuboid here, guys. So this side here is FR. It is the same as this side FR. So if you consider this triangle, so this side is FR and this side is FT. And in the transverse plane, we have another angle. It is called the transverse pressure angle. So for the gears, for the helical gear, we have two pressure angles. One is the normal pressure angle in the normal plane, and one is the transverse pressure angle, which is in the transverse plane. And then based on this triangle here, okay, you can find that tan phi t based on this triangle is equal to FR divided by FT. This is one equation. And then based on the previous equations, we still can find, if you go back here, you will find the relation here, this equation number 5. There is a relation between FR and FT. So if we take this equation number 5, then go here and take this equation that is based on the triangle in the top equation here, that is based on the triangle in the transverse plane. So we can find the relation between these two pressure angles between phi n, which is the normal pressure angle, and phi t, which is the transverse pressure angle. So based on, if you equate these two equations, you find from equation number 5, Fr over Ft, and equate these two equations, you will find that tan phi n, which is the normal pressure angle, is equal to cosine alpha, which is the helix angle, multiplied by tan phi t, which is the transverse pressure angle. So what we have here, look, let's focus on this plane. This plane, connect these lines together. Okay. So what we have here, we have E, F, C, D. Okay. This plane is called the transverse plane. Okay. Transverse plane means that it is perpendicular to the center line of the gear. Okay. So in this case, this component of the force, Ft, is going to be perpendicular on the center line of the gear as well. Ft, this force Ft, tries to rotate the gear. So this is the force that that we normally use, or when we have a torque here. We use this torque to calculate the Ft. So it's like as if you have this is the pitch circle, and then you have Ft in this direction. It is tangent to the pitch circle, but at the same time, it is perpendicular to the center line. Okay, and it is calculated based on the torque. Okay, and the diameter of this pitch circle. Okay, right. So if we, in this plane, in this EFCD plane that is perpendicular to the center line, if we take this triangle, this triangle is, which is EFC, okay, EFC. Let me just clear this so that you can see it. So let's take EFC. So if you connect this E point to C point, this is going to be in the plane, and the angle between this line and the force Ft here, the angle between the Ft and this line is called phi t. So phi t here is nothing but the transverse. It's called the transverse pressure angle. Okay. So what we need to do here, we just need to find the relation between the transverse pressure angle phi t and the normal pressure angle phi n. This normal pressure angle phi n is the angle between Fn here and the horizontal line BC, okay, based on this graph. So based on this triangle here, you see, take tan phi t. So tan phi t is equal to Fr over Ft, okay? So this is the equation that you get from this triangle. I have to go back here. And then remember that I have another equation here. I have this equation. So I can say Fr over Ft is equal to tan phi n, okay, divided by cosine alpha. I'll take this equation, go here, okay? And this is the equation that I've just written on the previous line. And then you would have here, you just divide by divide by Ft. And then equate these two equations. So tan phi t eventually is equal to tan phi n over cosine alpha, right? And then eventually you will have this equation here that relates phi n to phi t.